All right. Um, so this is just kind of a very high level introduction to what a dictionary is, also known as a map in the standard template library. So the word search key here is important, right? So in a dictionary, each item in the dictionary is going to have a search key, and that is going to be how we know how to store that particular item and how to look it up later. Um, so here's just an example of what we might put in a little dictionary. In this case, the search key would obviously be the city, right? And then the other two columns are just information about each city that we would be storing alongside the search key. So here's just a list of the different dictionary operations we're going to want. Test whether it's empty, get the number of items, insert a new item into a dictionary. The interesting ones are going to be the ones that involve the search key, right? So by interesting, I mean different from what we've seen already this semester. So remove the item with a given search key from a dictionary. And then get the item with a given search key from a dictionary. And then this one doesn't mention search key, but when we insert a new item into the dictionary, we are going to do it based on its search key, right? Test whether a dictionary contains an item with a given search key. And then this one's interesting, right? Traverse the items in a dictionary in sorted search key order. So presumably, if we know that our client is going to want to do this, especially if they're going to want to do it often, we're going to want to use a binary search tree to implement our dictionary instead of using a hash table. Okay, so here's what they always do in the text every time they introduce a new abstract data type. They first list it out informally like this, then they list it more formally like this. These are the same functions, just with more specifics and done more formally. And then we can skip over most of this, but so here's our interface. And so for the assignment, we are going to be using this interface for the dictionary abstract data type. So there it is, nothing too new. Now what he's going to do in the textbook is he's going to go on at some length about different possible implementations of a dictionary. And obviously, when we're talking about implementing a dictionary using a binary search tree or using a hash table, we are talking about those are the good implementations, right? He's actually going to talk about the possibility of just implementing a dictionary using a basic array implementation or linked based implementation. And that's fine. And he makes the point that, if your data set is always going to be fairly small, it probably doesn't matter all that much. And that's true. But I'm going to, for the most part, I'm pretty much going to skip over that, right? It would just be each element in the array or each node in the linked list would have two parts. It would have a search key part and it would have a data item part. And that would be pretty much all there is to it, right? If I was storing it in an array, which is very small. Oh, what is very small? Oh, that's a good question. Honestly, probably you could have, and well, it also depends on how fast you need your um, your algorithm to go, and it also depends on how often you're going to be doing the finding. For example, maybe you're in a situation where you need things to be very fast, and not only that, but you're doing operations that where each operation requires that you find 100 different entries. So there really are a lot of factors that go into what constitutes very small. So I'm not quite sure if I can give you a really solid answer to that. Um, but I would say you're probably safe. It would probably be safe to say that if it was a few hundred, that would definitely be small. Probably even a few thousand. Um, anyway, so I'm hoping that this makes sense. Basically, this is just um, an array implementation or a linked-based implementation would be storing the items just the same way we've done several times now in this class. The only difference being that each entry or each element of the array or each node in the linked list would have two parts, a search key and the data itself. So then looking at the array implementation as an example, if we store it this way and then we need to find something in the array, that would actually be fairly efficient, right? It would be a logarithmic algorithm because we could use, if we store if we store the items in the array sorted according to their search key, then we can use a binary search to find the item. One disadvantage of the array implementation is the whole size thing, right? Even if it's a dynamic array, you may find yourself having to increase the size of the array at some point. But for the most part, if you can predict fairly accurately what the maximum size of your data set is going to be, this is not a bad implementation if you're doing a lot of finds. Now, if you're doing a lot of inserts, that's another issue, right? Because we're keeping it sorted. Every time you do an insert, that's a linear, a big O of n operation, right? Because every time you do an insert, you have to shift everything down in the array. So anyway, we're not going to talk too much about these sort of basic, not very fancy implementations of a dictionary. So that means I'm going to skip ahead. By the way, before I skip ahead, if I'm not mistaken, this class right here called entry, we're going to use this class in our assignment, even though we're going to be using a hash table. The entry class is still going to be the same. So it's pretty basic. It's just two data members, the item itself, and then the search key, and then constructors, accessors, a mutator, and then a couple of functions to test so that we can make sure that we keep the items sorted. Okay, so here's a picture of what it might look like if we implement it using a binary search tree, using the ... to indicate that there's going to be more here than just the search key, right? There's also going to be some data. So here he's going to spend a whole section showing you a sorted array-based implementation of a dictionary. I'm going to leave that for your own reading on your own time. And then we're going to do the same thing using a binary search tree implementation. I'm going to leave that up to your own reading. And then we are going to jump ahead and talk about, I think the next thing is going to be hash tables. Okay, so here we get to the section about hashing. And I have to apologize, but I'm going to have to take like a 3-minute break here. So hold on for a couple of minutes and I will be right back. Okay, I am back. All right, so I kind of gave you a little introduction to hashing already. Basically, so here's one important thing to understand. Understand that what a hash function is. So a hash function is a function that takes a search key and translates it somehow into an array index. So if we have a perfect hash function and we can translate every search key into a different array index, then we're done, no problem, right? However, that situation is very rare. Typically, what the situation is that we have the possibility that several different search keys could get translated into the same array index. So basically, there are two issues to try to figure out when we are designing a hash table. The first issue is what's the best hash function going to be that spreads the array indices out as much as possible. The second question is, what are we going to do if we have two search keys that both end up going to the same array index? And that's called a collision. So issue number one, get a good hash function. Issue number two, how do you handle collisions? Okay. So let's see what we talk about here. You can see here he's calling it an address calculator. That's what I'm talking about when I talk about the hash function. Hash function, hashing, hash table, stuff I've already talked about. So here he's talking about the perfect hash table, hash function. That's what I was just mentioning about where every search key goes to a unique array index, but that's pretty rare. So usually we end up with having to determine what we're going to do about collisions. Okay, so examples of hash functions. So if your search key is the 9-digit employee ID number, you could select the 4th digit and the last digit to obtain 35 as the index to the hash table. Okay, as far as I know, that's pretty random. It's just kind of demonstrating that, you know, there's different ways you could do this. Not saying this is necessarily a particularly good way to do it, but just to kind of give you a sense of what a hash function might look like. Okay, one way to improve the previous approach of selecting digits is to add the digits. So we could just add all the digits together and use that as the index into the table. So that's a second example of what the hash function might do. So modulo arithmetic is used a lot in hash functions because whatever your hash function is, you have to make sure that it results in indices that are valid, right? So if you do your hash function and then when you're done doing your hash function, you just do modulus table size, that's a way to make sure that the result is a valid index. And as a matter of fact, one possible hash function is to do that and nothing else, right? Just take whatever, assuming it's an integer, take whatever the search key is and do a mod table size on it. Okay, so here what we're getting to is, okay, what if the search key is not an integer? What if the search key is a string? So I think I mentioned earlier that one idea would be to just add up the ASCII values of the letters in the string and use that as the index into the array. All right, so he's going to talk about this thing called Horner's rule here. I'm not going to talk about that right now. I'll talk about that next time. Okay, so that's all we're going to talk about in terms of hash functions for now. Any questions before we move on? Okay. All right. So techniques for resolving collisions. So here he says, 2 general approaches to collision resolution are common. And I have to say that The organization here is a little bit confusing. Well, at least I got confused, so I'm just going to put it out there for you. He talks about two approaches. The first approach is right here, but this seems like kind of the type of heading that would only like be the heading for a paragraph or two. It turns out that this is the heading for like the next 3 pages or something, right? It doesn't get to approach number 2 until down here, like 4 or 5 pages later. Okay, so just to know that these 1, 2, 3.5 pages are all explaining open addressing. Okay, so first, most simplest option under the topic of open addressing is that it's called linear probing, and that just means that if you go to insert an item in your dictionary and you use a hash function and the index that the hash function that returns turns out there's already an item there, then you simply add one to the index and put your item in the next element after that in the array. Then if there's already an item there, then you add one again and try that next one. And if there's already an item there, then you add one more and try that next cell. So that it should make sense why that's called linear probing, right? You're probing, meaning you're looking for an empty, unused spot where you can store your item. And if you when you find that the cell you're looking at is already taken, you just move on to the next cell after that until you find one that is not being used. Okay. I'm looking for this. So here's an example of, let's say that all of these 4 search keys ended up giving us an index of 22 when we put it into the hash function. So the first number was 7597. The second search key was 4567. We couldn't put it in the 22, so we added one and put it in the 23. Then the next search key we got was 0628, which also mapped to index 22. So we couldn't put it in the 22 because it was already used. We couldn't put it in the 23 because it was already used, so we put it in the 24, and so on. The problem with this approach is that in practice, you end up with something called clustering. So one of the problems with the linear probing scheme is that items tend to cluster together in the hash table. So this is called primary clustering. Clusters can get close to one another and in fact merge into a larger cluster. And so it turns out to be a fairly significant problem. There's something else I wanted to mention here. So it can get a little confusing because how do you know whether a particular cell is being used or not? You're going to have each table location is going to have to keep track of whether it is available or not. But then there's this even further complication. If you put something into a cell and then you remove it later, hold on, my brain is short-circuiting here a little bit. Let's look at this paragraph. The remove operation is no problem. You just find the desired item, as in get item, and remove it from the hash table, making the location empty. But now what happens when get item needs to locate an item? The new empty locations that remove created along a probe sequence could cause get item to stop prematurely. right? Does that make sense? So if you've got this string of 4 items here that all have the same hash code, and then let's say I'm looking for the 0628, the way that would work is I would first look in spot 22. That isn't what I'm looking for, so I'm just going to probe until I find it, and then I find it at location 24, right? But how do I know when to stop looking? Well, naturally, I would stop looking when I got to a cell that was unused. That would tell me to stop. But that might be wrong if I'm looking for, let's say I'm looking for the 3658 and the 0628 has been removed. When I'm doing my linear probe to find the 3658, I might get to location 24 and say, okay, well, this is an unused cell, so the number 36, the search key 3658 must not be here. That concept is not as complicated as I just made it. Does it make sense, or should I try that again? I want you to understand what the problem is here, why we can't just have 2 states, used and unused. Anybody want me to try that again? All right, I will assume that it is clear why it does not work to have just 2 states, either used or unused. So the way we're going to solve this is we're going to have 3 possible states, either occupied, empty, or removed. So if it's removed, that means we can put a new item there if we want to, but it also tells us that if we are looking for, if we're trying to look up a value, we need to keep going. We can't just stop there. Okay? All right, so this gets, as you can see, hash tables can be extremely efficient. Yes, but also can get pretty complicated, right? There's going to be a lot going on here. Okay, so let's deal with the problem of clustering. The solution to the problem of clustering is when you are looking for a place to put your item, instead of just going to the next cell, in other words, adding 1 to the index, you're going to add 1 squared to the index, and then add 2 squared to the index, and then add 3 squared to the index, and so on, right? So one way to look at linear probing, the first technique, is that if the cell is already taken, add 1 to the index. Then if that cell is already taken, add 2 to the index. Then if that cell is already taken, add 3 to the index. With quadratic probing, what we're going to do is, if the original cell is taken, add 1 squared to the index. If that one's already taken, add 2 squared to the index, and so on. So we would do index, look at the index. If it's already taken, we would do index plus 1. If that's already taken, we would do index plus 4. If that's already taken, we would do index plus 9, and so on. So taking these same 4 search keys here that all collided at index 22 and using a quadratic probe approach instead of a linear probe approach, we get this, right? The first one goes in the 22. The second one goes in the 23. The third one's going to go in 22 plus 4, which is 26. And then the fourth one is going to go in 22 plus 9, which is 31. So it spreads them out a little bit more. Okay? Any questions about quadratic probing? All right. I'm going to skip double hashing for now. Okay, here's a little section on increasing the size of the hash table with any of the open addressing schemes. So linear probing, quadratic probing, and then this thing called double probing that we're not going to talk about today. as the hash table fills, the probability of a collision increases. At some point, a larger hash table becomes desirable. And then we've seen this many times, right? With both stacks and queue implementations, I believe I had you increase the size of the table when the dictionary becomes too full. It's a little more complicated with a hash table. The main thing that's more complicated is that we can't simply move the items from the original hash table to the new hash table because they're going to have different hash values now, right? So if, as is typically the case, we find the location where we store things by using modulus, the table size, if we make the table bigger, everything is going to go into a different location. So when we rehash, that's what this process is called. We decided that the number of items in the hash table is too many to remain efficient. We need to make the table size bigger. Basically what we do is we're going to have to start over from scratch, run every single item back through the hash function to get a new location for it and store it, basically just by calling the add method. Okay, so that is a really inefficient, time-consuming task, something that you definitely do not want to do often, and hopefully find a time to do that when you're not busy at the same time trying to do a bunch of adding and finding. Okay, so that's the discussion about open addressing. Okay, so that was approach one. Let me actually skip ahead a little bit and show you a cool graph. Okay, here is a graph, the relative efficiency of 4 collision resolution methods. And as you can see, we're sort of doing them in order of how efficient they are, right? Linear probing is up here, quadratic probing is here, separate chaining, which is what we're about to talk about, much more efficient in general. Okay, so having said that, that was just sort of a my attempt to sort of motivate you for watching what we're going to be doing next, and also this is the technique that we're going to be using in the assignment. He calls this approach to restructuring the hash table. Basically, what that means is that instead of making the hash table be just an array of entries, we're going to make it so that each element of the array can accommodate more than one item. And then one way to do that, which we're just going to mention and then throw out, is that each element in the table could itself be an array. Okay, so then we would, if we have more than one item that hashes to the same array element, it's okay because each array element is actually an array of elements, and so we just stick it in that array. But that's actually not a great solution. The better solution is this picture right here. And if you get anything from today's discussion, just printing this on your brain somewhere is what you want to do. This is called separate chaining. And basically what it means is that each element of our hash table array is actually a pointer to a linked list of all of the items that hashed to that same index. Okay, so the way we're going to resolve collisions is we're just going to make a linked list out of those items that hashed to the same array index. Make sense? Any questions about that? And that actually as I showed you in the diagram, usually works out pretty well. Let's talk about worst case scenario just for a second, right? The worst case scenario now is everything in our data set hashes to the same index, in which case we just have a linked list, right? So that's where, remember, if you remember back to when we were looking at c++.com, it said worst case for finding something in the unordered map was big O n, linear. And that's the situation where everything hashes to the same array index. So you just get one big long linked list.
I have a quick question.
Yes.
Is there, for the length of the linked list attached to each hash node, I guess you call it, is there any constraints that we should be putting on those lengths compared to the length of the hash, the length or the number of nodes in the hash table itself? Or because it seems like at what point is there like a agreed upon point where you start cutting those linked lists in half and creating new hashes for it? Or how does that?
There really isn't a technique for that.
Okay.
That's sort of the one of the advantages of having a linked list. But so the strategy is more along the lines of just making sure that your hash function,
disperses it enough so that you're not getting some crazy long linked list. Okay, so it's more, if you did it right, it's not a problem you'll have to encounter.
Yes. Although, that may be a little bit of an oversimplification because you never know, right? But yeah, that's the idea. There's really no way to, I'm just kind of trying to take your suggestion and run with it. And basically, I guess what that would mean is that if one of the linked lists got too long, you would just have to change your hash function to something else in the middle of your algorithm. I suppose that's possible. I suspect that it turns out that it just works better to work more on making sure that your hash function isn't going to do that to you in the first place.
Gotcha. Thank you very much.
There's certainly, there are still people out there doing research on hashing and hash tables and hash functions. So, new ideas are always being explored. So, all right, good question though. I mean, the question itself makes me feel better about that it sounds like people are understanding what's going on, because it's a suggestion that makes sense. Okay, so I don't think there's too much more to what I have to say here. Basically, I just throw this picture out at you, and inserting is never a problem, right? Because you can always just insert at the front of the linked list. So the only problem could be if you get a linked list that's a little bit long, but the probability of that happening is extremely small. All right, I'm not going to talk too much about this mathematical analysis, and I think that I'm going to stop there for today. Anything else you want to talk about? I guess we could look, oh, you know what, I haven't even put the assignment up yet, so I will put the assignment up sometime in the next couple days, and then maybe next time we can look at the assignment a little bit.
I know you're removing it from the actual docket, but is there any way you could put up the assignment for heaps just so we can get some practice with it if we want to work on it? Because I think that's the one that got removed. I'm not positive.
Yes, that is the one that got removed. I don't actually have an assignment, but I'm sure that I could just look in the text and find something good that would be good.
Sounds like I could probably do the same though too. Just check out the programming questions and grab it from there. But thank you.
Sure, yeah. Let me know if you look and you're not quite sure what to do with that. But yeah, I chose notice I skipped a chapter. I chose to hashing and dictionaries instead of heaps because, believe it or not, hash tables is actually on the course outline for the, I'm not sure if you guys are familiar with the CID numbering system, but the computer science California ID number for this course is Comp 132, and that course descriptor for the statewide system mentions hash tables and does not mention heaps. So that's why I chose hash tables instead of heaps. Anyway, anything else you want to talk about before we sign off? All right. Hope it's going okay with the binary search trees. Let me know if not. And I will see you next Tuesday.
Thank you, Dave.
Thanks.